state level, again, when you think about how you're going to lay down your coverage, whether it's from wireless or space, again, very highly concentrated. Even if you go on a metro level, and this would be, say, the Los Angeles region, again, very highly concentrated. So this, is obviously in the wireless world, first order way to deal with this would be through the placement of all of your cell towers and your resources, and it's reflected in spectrum pricing. For satellite, think of it as frequency reuse, think of it as beamforming. You need to be able to place your bandwidth quite precisely if you want to have it used the most. Now, one of the things I think that people will say is, well, why are you so focused on where all those people are? Isn't the demand for satellite going to be where people aren't? And that's one of the things that I think people really don't appreciate about the satellite business. So I'll show you some of our experience in the US. We are also providing the network infrastructure for Australia's national broadband network, which has a satellite component. That satellite component is intended to serve about the last 3% of the population in Australia. So 97% is intended to be served by either terrestrial or wireless. And what this map shows is a map of the satellite beam coverage in Australia. The blue beams are larger ones, and those are areas where they need less bandwidth, they have less demand. The red beams are the smaller ones, are higher density. And so when you think about the amount of satellite bandwidth per unit area, those are the places where there's most demand. And what you can see is the places where there's the most demand for satellite bandwidth are in the places that are the most populated. And that's especially true in that southeast corner where Sydney, Canberra, Adelaide, Melbourne are. And what's really interesting about Australia, unlike other markets, because Australia had a single telecom company, Telstra, all of that demand is based on actual addresses. It's not based on estimates of demand or surveys. It's based on computing what the cost would be of providing these other forms of telecom to people, and then putting satellite in. Their algorithm was to apply satellite for those that were the most expensive. And turns out that the areas where they're the most stressed, that is, they're having the most difficult time providing sufficient supply to meet the demand, is in the most populated areas of Australia. In the US, we have a lot of experience in the US. We don't have the benefit of having the addresses of everybody and knowing what their connections are, but we've gone about it a different way, and that is since 2006, we've provided satellite broadband service in the US. I'll talk a little bit about that. First way we did it is we basically covered the whole country. And what you'd see, and going back to that population distribution of the US, what you can see is population is concentrated, and that red line is to give you a sense of sort of the portion of the population, think of it as a cumulative density function, as a portion of the population relative to geography. First thing that we did was a satellite called Wild Blue 1, which was a 32 beam, spot beam satellite, covered the entire US. We put out offers and said, if you'd like satellite broadband, at that point it was half a megabit for about $50 a month, raise your hand. And what you can see is that orange is those are the places where people first said, hey, I can't get broadband, I'd like broadband. And what you can see is that by covering the whole US with a relatively uniform grid of beams, that's turned out, a little bit surprisingly, to be not a very good approximation to what the demand is. That is, we didn't match where we put our bandwidth to where people were asking for it. So we learned from that. We did another satellite that was launched 2011 called ViaSat 1. Now this one had a lot more bandwidth. We were able to offer at the same price 12 megabits per second down. And taking advantage of what we knew about the population, we basically focused all our bandwidths in the most populous states and put essentially none. We did some tricks in frequency reuse to augment the bandwidth in the high demand areas at the expense of the low demand areas. It's a better approximation to what the demand was. Still wasn't really good enough in that we had way more demand in higher population areas, less demand even in the areas that we covered, which were more of the high population areas. We still had excess bandwidth in some places, conditioned on the offer that we were going to make. Now, our next satellite, ViaSat 2, still under construction, will be launched next year. We did a couple of big improvements. One is much larger geographic footprint. So now we could cover not only all of the United States, but large parts of Latin America down to the northern edge of South America and the oceans all the way across to Europe. And what we believe we've done is we've given a much better approximation of the supply of bandwidth, and we've also been able to greatly increase the capacity of the satellite. And I'll give you some numbers of that. With this one, we expect to be able to go out and make offers for about the same price of 50 to 100 megabits per second per user in many places. So we felt like we were making good progress. Recently, there's been a lot of interest in low Earth orbit, non-geosynchronous satellites. We thought, even another one of Will Rogers saying, even if you're on the right track, you'll get run over if you just sit there. So we're looking hard at go back to fundamentals. Is it better to do non-geosynchronous satellites or geo, and come up with ways to compare those? So just to review quickly, you think about satellites. People are generally looking at, for communications purposes, 3 forms of orbits. The ones that would be closest to the Earth are called low Earth orbit. Then you'd have medium Earth orbit. Low Earth orbits would be in the hundreds of miles above the surface of the Earth. Medium Earth orbit would be in the thousands, low thousands of miles above the surface of the Earth. Geosynchronous orbits, 22,500 miles above the surface of the Earth. Although the satellites I showed you before are geosynchronous. And think about the two extremes. With the low Earth orbit satellite, people are looking at hundreds of satellites to provide continuous coverage around the world. And you might see those satellites would be uniformly distributed in orbit space, tend to cluster around the poles a little bit. You can see that distribution there. With the geosynchronous ones, 3 geosynchronous satellites can essentially cover the whole world. So one of the points people might think about right away is that there's some benefit from a power density perspective of being closer to the Earth. And one of the things to think about with satellites is it's all solar powered. So we think of the satellites as a factory. What you're trying to do is you're trying to turn photons into electrons. You're going to turn those electrons into power flux density on the surface of the Earth. And then in order for this thing to be a good economic tool, you need to turn that power flux density into bits and dollars. And you can then figure out whether you can use those dollars to get a return on capital or to make cost of really, really affordable bandwidth for lots of unconnected people. And when you think about it a little bit, what you realize is that really in turning that power into the power in space from your solar panels into power flux density on the Earth, the altitude doesn't matter at all. Of course, there's a path loss component, which is like an R² component. So the farther away you are, the worse off you are in terms of generating power flux density. But on the flip side, there's also an antenna solid angle effect. And so by being farther away, if you're trying to cover the same geography on the Earth, you're going to subtend a much smaller portion of the solid angle, and the effective isotropic gain of that antenna compensates exactly for the path loss. So that when you're thinking about especially the way I described the problem, which is your real problem is to match power flux density, which is your supply, to demand, and demand is based on the geography. There really is no benefit to being closer to the Earth. As a matter of fact, there's a big issue with being closer to the Earth, and I'll show you. So think about it these 2 ways. One is the 2 extremes being the geosynchronous one and the low Earth orbit one. Geosynchronous on the left, you take a look at what you can do, so you can see each of those satellites has a field of view, which is essentially a third of the world. And so that one satellite, if you do think of it as a beamforming problem, if you can make thousands and thousands of beams, you have, from that one satellite, the ability to shape your bandwidth demand very, very effectively to match what that demand is. The issue when you're really close to the Earth is that most of the satellites can only see a very small portion of the Earth. And so you could have all of the beamforming capability you can imagine, but you can't put it outside of the field of view of that satellite. Of course, 2/3 of the satellites or more are going to be over water, and then you've got desert and lots of unpopulated areas with very, very small demand. So when you think about it, and it's very interesting when you're thinking about terrestrial radio broadcasters with tens of kilowatts, to put, if you think of it this way, to put 60 kilowatts in space, that's a lot of power. And you would get no more power flux density from 60 kilowatts in geosynchronous orbit, no more flux density from low Earth orbit than you would say from geosynchronous orbit. In a geosynchronous orbit, you have the ability to see every place. With a low Earth orbit, you're really limited to that field of view issue. So the problem, it's not impossible, it's a lot harder when you get a lot lower. The other really big thing that's important about the geosynchronous satellites, and this is, when you think about adoption, geosynchronous satellites, because they hang in one place in the sky, are really, really easy to aim at. And so when we think about connecting people, you want them to be empowered to go solve this problem themselves. You can see in many, many parts of the world, satellite TV is by far the best and most cost-effective way for people to get TV. Those same types of antennas that you can put on the side of a building, because you only have to look in one direction, are a really, really good way to reach these billions of people that are still unconnected. The other really big thing you have to think about from a technical perspective is think about the differences that have gone on in terrestrial communications between broadcast and unicast. And one of the big issues in the satellite domain is the satellite industry economically has been dominated by broadcast for decades. So most of the work that's been done in trying to apply satellites to communications has really been repurposing broadcast satellite technology. And this is a picture of, on the right, you can see about almost half of the payload of the ViaSat 1 satellite. That was that 72 beam satellite, had about 140 gigabits of throughput. So it's still, today, the most productive satellite ever built in terms of telecom capacity. But it's really built out of distributed microwave tube technology, and making all those beams is essentially a big exercise in multi-feed antenna arrays. And you can see on the upper left is sort of the waveguide. It's the waveguide map of that satellite. So if you were to try to take that, which is a few dozens of beams, and scale that up to thousands of beams, you'd see it's impossible. What you really need is a totally new technical paradigm for building satellites if you want to get the type of frequency reuse and economics that are possible in providing unicast communications. So that's what we think is the most important problem in connecting people by space. It's figuring out how to transform that way that you build satellites and getting large single beams or a few dozens of spot beams into getting thousands and thousands of beams that'll let you get enormous amounts of frequency reuse. And as we all know, if you're power limited, you can grow communications capacity like the log of increasing power, but you can grow linearly with spectrum. So if we can reuse the spectrum, that is by far the most cost-effective way to grow capacity in space. And that's going to be through frequency reuse tailored to match population density. So this is give you an idea of what you can do working within the constraints of what you can put into space quite cost effectively. So what I'm showing here are 4 attributes of a number of different types of satellites. In each cluster, starting on the left with a conventional Ku-band broadcast satellite, what you'll see are those 3 bars reflect power, how many watts they have, what the cost of getting that satellite is, building the satellite, and then the mass of the satellite. And then the white line is the capacity of the satellite in gigabits. And what you see is, starting on the left, conventional Ku-band satellites have been on the order of a gigabit per second, and just consider that to be sort of a unit in power, cost, and mass. Spot beam, small number of spot beam Ku-band satellites, a lot more expensive, not a whole lot more power, not a lot more mass, not a lot more bandwidth either, maybe single digit, 10 gigabits a second. The first global Ka-band satellites, I-5, again, single digit gigabits per second, a little bit more expensive, a little more power. ViaSat 1, what we did relative to them is about the same amount of power, maybe a little bit less, way more bandwidth. You can see that was about 100 gigabits per second of throughput, not a lot more mass, not a lot more power. See ViaSat 2, ViaSat 3 class, which is the thousands of beam satellite that we're doing, we're going to use a lot more power, a lot more meaning about double the power of a conventional satellite, a little bit less. Mass, pretty comparable. Cost, a little bit higher, but literally 3 orders of magnitude greater throughput with much more flexibility in where to place that. So one of the things people ask about is, hey, what about latency? Latency's got to be a huge problem, 22,500 miles. So above the Earth, long propagation delays, how does that relate to the communication that you're trying to provide? So one of the things that we point out that's really kind of interesting is if you look at the history of terrestrial communications, historically, the things that have improved speed or total bandwidth capacity have also improved latency. And there haven't been a lot of times in developing telecom systems where we've had to make a choice, where latency had to be traded off against speed or bandwidth. So what happens if you do present that choice to people? What would they choose? And one of the things that's really interesting is one of the most compelling and visible applications of our high throughput satellites, these very high capacity satellites, has been in in-flight Wi-Fi. Obviously, in-flight Wi-Fi is a very difficult problem to solve terrestrially, but the first mass market application of that in the US was through air-to-ground cellular. And what's interesting is there are websites that rate in-flight connectivity on airlines now, just like they'll rate the seats or the food or their entertainment options. And in the US, there's a website called Route Happy, and the service that gets the highest rankings is the service that's done on our satellite, and it's available on JetBlue and some United Airlines flights. That gets the rating of best Wi-Fi. What's interesting is the service that's rated as the worst Wi-Fi is the air-to-ground system. That's the one that has the least latency, essentially no latency. The problem is it has very little bandwidth as well. And for any of you that have done the modeling of throughput versus delay knows that the failure mode of not having enough bandwidth is that delay grows without bound, right? And that's what you're seeing. So it's pretty easy to get delays when you don't have enough bandwidth that are far worse than the latency that you'll see through satellites. And what you think about what we started from it's about providing affordable and fast communications. It's not just providing that communications at all. So now, yes, we think that more bandwidth is better and that latency is tolerable, but what we really have been working on along with the density on the satellites is how to mitigate the effects of latency in the real world, and that's especially in web responsiveness. And that problem has been a little bit exacerbated by increasing demands for privacy and end-to-end security and encryption. So one of the ways on our older systems that we could deal with latency is essentially through a look ahead by trying to anticipate what we call prefetching those sites that are likely to be viewed based on what a subscriber is doing. And you can do that based on the content of what they're working on. When things are encrypted end-to-end, you no longer can do that. You can't do the look-ahead anymore because you can't see it. So you need to work purely from context. And think of it as having a little agent that works for you terrestrially, and that agent on the ground is not subject to the satellite latency. So he can assemble all the different sources of information that goes into web pages and then provide that in a single satellite hop over a satellite with only one amount of latency. The end result of that is we should be able to deliver web pages within about 1 or 2 round trips, which is about a second or two. And that's actually pretty fast compared to the way websites are served conventionally, even over zero latency terrestrial solutions. And to give you a sense of what that can be, we put together a little video of our current work on there. That'll give you a quick sense of what it is that we're doing. And what you're going to see here, first clear a cache so there's no stored content in here. Then we're going to go to 4 different kinds of websites. That's just the browser. We're doing this on a variant of Chrome. And the first one is an Apple website. So what you saw there, somebody typed in apple.com, and see how quickly that website loads over satellite, despite having lots and lots of components to it. We'll do it again with ESPN. Now these two are both HTTP websites. They're not encrypted, but it gives you a sense of how quickly you can load, how responsive things can be, even with satellite latency and with very rich content from lots of sources. Now these next two are HTTPS websites. So we're going to load a couple of those. The first one is Etsy. And you see someone type that out, but this time with an HTTPS. And again, really, really quick response. Most people, and this is sort of exactly the situation that we see on things like airlines, is that people really respond to having material appear in front of them really quickly. And here's Amazon again through an HTTPS. So in summary, I think the things that we see as being the ingredients to deliver truly affordable, high-speed internet from space, number one, it's really effective satellites. A couple of other dimensions that I didn't talk about, but that come along with the approach that we're looking at is one is much lower cost infrastructure. So we can put very low cost satellite infrastructure right on the best fiber access nodes. Actually, we're looking at delivering that through Wi-Fi because it turns out the cost of delivering this bandwidth, when we're looking at ViaSat 3, over 1,000 gigabits per second in a single satellite, delivering speeds to individual terminals of up to 300 megabits today. Costs can be so low that we're really looking at delivering that through Wi-Fi to avoid the costs of the terrestrial cellular operators. That we can deliver it very, very cost effectively in the same way as a satellite TV. Going to allocate that bandwidth wherever the demand is, including in remote areas, but especially expecting it to be where the people are. Deliver speeds, I mentioned, in the hundreds of megabits. Volumes that are essentially unlimited for people. Excellent for providing video. Bandwidth is low cost. Coverage is everywhere. Very responsive. And that we can deliver it where that demand is. So that's our view. Thanks very much. Really appreciate your time and attention. I guess I have a couple minutes to take questions, if there are any.